Illustration of matrix chain multiplication. In the last lecture, we learned about matrix chain multiplication problem. What did we learn? We learned that this problem is of finding the optimal way to parenthesize a sequence of matrices, let us say A1, A2, A3 and so on, such that when you multiply these matrices, you should be able to do with minimum possible number of scalar multiplications. What did we learn about scalar multiplications? Depending on the way you parenthesize, that is whether you do A1, A2 and then multiply it with A3, or you do A2, A3 and then multiply A1 with the result of A2, A3, the number of scalar multiplications that are done as part of this chain matrix multiplication will differ. So if there are a lot of matrices in sequence, let us say A1, A2 up to AN, a lot of matrices, then the number of scalar multiplications will differ very largely depending on whether you parenthesize this correctly or you are making wrong way of parenthesization. Whatever way you may parenthesize, final answer will be same, but the number of scalar multiplications that are required in order to reach the final answer, that will differ. So let us see what we learned in the last lecture. If you want detailed explanation on the algorithm on how the approach is to be done, please refer to the last lecture. Here we are going to have a complete illustration of how that algorithm runs by taking an example. Okay. So the first thing, what did we learn in the last lecture? We have to construct a dynamic programming table. We'll be solving this using the approach of dynamic programming. So we'll need a table which is of the size n by n, where n is the number of matrices you want to multiply. In this DP table, what will you do? You should have a base case. Our base case is DP of I is equal to 0. What does this signify? This signifies that whenever you have only one matrix, what does dpii signify? In order to understand this, you need to know what does dpij signify. This signifies the minimum number of scalar multiplications that are required in order to multiply matrices from ai till aj. Let us say you have a lot of matrices in the sequence, actual sequences from a1 till an. In this, if you take one part which is from ai to aj, what is the optimal parenthesization and what is the minimum number of scalar multiplications required? That count is what dpij represents. So dpii says starting from ai and ending in ai, which means there is only one matrix, and that is why dpii is 0. Next thing is, what is the recurrence relation? We found a recurrence relation in the last lecture, that is dpij. This is the core part of this algorithm. In our recurrence relation, we wrote it as minimum of I less than or equal to k less than j. What is k? K is the point of split that we are considering. It should be dp of ik, which is the number of scalar multiplications required to multiply all the matrices from ai till ak, and then plus dp of k plus 1j. What does this signify? This is the total number of scalar multiplications required in order to multiply all the matrices from k plus 1 to j, ak plus 1 to aj. And then finally, after you have this part and this part, you have to multiply both those parts. In order to do that, what did we learn? It should have a total of pi minus 1 into pk into pj number of scalar multiplications. So this is the total number of scalar multiplications required. That is the minimum number of scalar multiplications required in order to multiply all matrices from ai to aj. What about the final solution? Final solution will be present in dp of 1 n. This is what we learned. In this lecture, what we are going to do is we'll take an example of 4 matrices and we'll see how to find out the best way to parenthesize and how to find out what is the minimum number of scalar multiplications. Let us start with this. What we are going to do, we'll have a DP table and we'll see step by step how each entry in this DP table is getting filled. This is the idea. First of all, I told you we'll be having 4 matrices. It will be A1, A2, A3 and A4. These are the 4 matrices we'll be having. Let us define sizes as well. A1 will take the same sizes that we saw in the last lecture so that it will be easier for you to relate. So A1 is 5 by 15. A2 is 15 by 3. A3 is 3 by 10. And A4 is 10 by 4. These are the dimensions of these matrices. That is, A1 have 5 rows and 15 columns. A2 has 15 rows and 3 columns and so on. Next thing is, we'll define an array P. So P will be the array which will include all these sizes. This is what we want. We don't want to know what exactly are these matrices. We just want to know what are the sizes. So P is an array. In this array, you will have entries as 5, then you will have 15, then you have 3, 10 and 4. This is the only input that you require in order to find the solution for matrix chain multiplication problem. Because you're not actually multiplying, instead you are trying to find out minimum number of scalar multiplications. For that you only need the dimensions. You don't need actual values in the matrices. Okay, just keep this in mind. So this is our array, which is the input array. Next step is we want to have a matrix. It is the dynamic programming table. How should the dynamic programming table look like? It should have 4 rows and 4 columns corresponding to the 4 matrices we are having. We'll draw this dynamic programming table. This is the dynamic programming table we are having. 2, 3, 4. I'm going to number all of these. When I'm numbering, keep in mind that when I say 1, that means A1. When I say 2, that means A2 and so on. 1, 2, 3, 4. So here 1, 2, 3, 4 signifies A1, A2, A3 and A4. Okay. Next thing is here also I'll have 1, 2, 3 and 4. So these columns and rows, they signify the matrices A1, A2, A3 and A4. Next step is we have to start filling the entries in these matrices. In the last lecture, what did we learn? The base case is dp of I is equal to 0. That is, whenever you have only one matrix, in that case, your total number of scalar multiplications required is 0. Where should you put this 0? dp of 1, 1 is 0. This is 0. 2, 2 is 0. 3, 3 is 0. 4, 4 is 0. This is your base case. This is because in all these cases, there is only one matrix involved. So there is no particular multiplication to be done. So total number of scalar multiplications is 0. Now starts the actual algorithm. We are going to fill each of the entries. Let us see how to start from. Next thing, we have to fill this diagonal. That is what we learned in the last lecture. After the main diagonal, we'll go to the next diagonal, next diagonal. Finally, when you reach here, you'll have the solution. This is the idea. Let us go to the second diagonal. This signifies all those set of matrices where a total of 2 matrices are involved. The first diagonal, this one signified those matrices in which only one matrix is involved. Those set of matrices in which only one matrix is involved. Second diagonal says those matrices in which 2 matrices are involved. Let us see which are the possibilities. One entry to be filled is dp of 1, 2. This particular entry. What does that say? That says multiplication of matrices from A1 to A2. How many matrices are there between A1 and A2? Nothing. Only A1 and A2 are there. So totally you have to multiply these two matrices. Let us see what is the count of scalar multiplications required. A1, A2, if you want to do this, what should be the count of scalar multiplications? It should be A1's size is 5 by 15 and A2's size is 15 by 3. Where did I get it from? From here. Here I have already mentioned what are A1 and A2. If I multiply these two, what is the total number of scalar multiplications required? It will be 5 into 15 into 3. So the total number of scalar multiplications, 5 into 15 is 75, into 3 is 225. This is the total number of scalar multiplications. What will I do? I'll mention it here, 2, 2, 5. Next entry is of this one, dp23. So what is dp23? dp23 says multiplication of all matrices from A2 to A3. There are only two matrices there. So how do you identify the sum required? Here it will be A2, A3. For this, in order to identify scalar multiplications, A2 is of size 15 by 3 and A3 is of size 3 by 10. So total number of scalar multiplications required is 15 into 3 into 10. So 15 into 3 into 10. Why is it this? That we have already discussed in the last lecture. 15 into 3 is 45, into 10 is 450. So the total 450 we'll be writing in this block. Next one is dp of 3, 4, this entry. That entry signifies the sum of the multiplication of matrices from A3 till A4. How many matrices are there? Only two. A3 is of dimension 3 by 10 and A4 is of dimension 10 by 4. So what is the total number of scalar multiplications required? For A3 to A4, 3 into 10 into 4. That is 3 into 10 is 30, into 4 is 120. So here we'll enter 120. At this point, we are done with all the matrix sequences which are having two matrices. Next step is this diagonal, which signifies all those sequence of matrices which are having three matrices as part of it. So let us go into that part. This time we have to fill this diagonal. Now it's going to get a bit more trickier than the last one. So this is how this algorithm progresses. That is why I wanted to show you this particular step. That is how exactly is the table getting filled. Because as you move from one diagonal to the next, it becomes slightly trickier. Next step is when length is equal to 3. There are three matrices involved. This is the diagonal we are looking to. What is this entry? dp of 1, 3. So 1, 3 says multiplication of all those matrices from A1 to A3. Which are the matrices involved? A1, A2 and A3. When you have these three matrices, the difference from previous approaches, previously when you were doing this, you didn't have any split. But in this case, because you have three matrices, you have a possibility of a split. That is, either you can split here, you can first find A2, A3, then multiply with A1, or you can split here and find A1, A2 first, and then multiply with A3. These are the two possibilities. So I'll name the split as K. K is equal to 1, K is equal to 2. These are the two possibilities. If K is equal to 1, you will be splitting here. If K is equal to 2, you will be splitting here. These are the possibilities. Let us see each of those cases and find out which is the minimum possible number of scalar multiplications. For the case A1, A2, A3, what do you want to find? You want to find minimum of, so here we already wrote the equation, minimum of all the possible splits. For all the possible values of K, we already wrote I less than or equal to K less than J. That is why K is 1 or 2, because your I is 1, J is 3, so K can be 1 or 2. For all of the K's, for each value of K, what do we have to do? we have to do dpik plus dpk plus 1j plus the number of scalar multiplications required for that particular split. This is the logic. Let us try to apply this. What are the possibilities here? There are two splits, 1 and 2. So minimum of, what is the first case? If you are splitting at 1, first part will be dp of 1, 1 plus what will be the second part? Second part will be dp of 2, 3, and then along with this, you want to add what are the total number of scalar multiplications required if this is the split. So here 1, 1 and 2, 3 means split is here after A1. In this case, first part will have dimension as same as A1, that is P0, P1, P0 by P1. For the second part, the result of second part will have dimension P1 by P3, right? So in this case, how can you find total number of scalar multiplications? It will be P0 into P1 into P3. This is one possibility. And what is the other possibility? Minimum of, one is this and second one is dp of, second possibility is that your split is after 2, your k is equal to 2. Then dp of 1, 2 plus dp of, what is k plus 1? If k is 2, k plus 1 will be 3. K plus 1 j, where j is 3, plus what will be the total number of scalar multiplications? If split is here, then this will be P0 by P2 and A3 size will be P2 by P3. So this will be P0 into P2 into P3. Let us substitute the values here. If you substitute those values, that is equal to minimum of, what is dp11? From our table, dp11 is 0. This is the value. dp11 is 0. dp11 is 0. I'll put 0 plus second one is dp23. dp23, if you see from the table, it is 450. So I know dp23 is 450 plus p0, p1, p3. From my p, this is 0, 1, 2, 3, 4. P0, P1, P3 will be 5 into 15 into 10. So if I do 5 into 15 into 10. And what is the second option? dp12, value of dp12 from this table, it is 225. So 225 plus what is the value of dp33? dp33, here it is 0. So here you can see this is dp33, value is 0. After 0, I have P0, P2, P3. So from here, P0, P2, P3. So it will be 5 into 3 into 10. This will be 5 into 3 into 10. What is the value here? It will be minimum of, first one, 450 plus what is 5 into 15? 75 into 10 will be, 5 into 15 is 75 and into 10 plus 450. So this will be 750 plus you have this 450. It will be total of 1200. And what about the second one? Here you have 5 into 3 into 10. 5 into 3 will be 15. 15 into 10 will be 150. 150 plus 225, total will be 375. So this will be 375. So which is smaller? You have to find minimum of these two, 1200 and 375. So minimum value is 375, which means your value to be filled inside 13, dp13 should be 375. So I'll fill 375 here. 375 is filled. Next thing is to find this particular block. It is dp24. So what about dp24? dp24 says you want to find out the sum of all matrices from A2 to A4. Which are the matrices included? There is A2, then there is A3, and then there is A4. There are two splits possible. One is here and the other is here. This first split means k is equal to 2. Second split means k is equal to 3. These are the two possibilities. Let us see what happens in both those cases. I'll erase these off. This is erased. And let us do calculations for the new set of matrices. A2 to A4. A2, A3, A4. If you are multiplying these, there are again two splits possible. One is here, one is here. We'll take k equal to 2 and k equal to 3. So it should be minimum of, what are the possibilities? If k is equal to 2, then first part will be dp of 2, 2 plus second part, the remaining will be dp of 3, 4, 3, 4 plus what should be the total count of scalar multiplications? Here the split is here after A2. A2's dimension is P1 by P2 and the resultant of this will have dimension P2 by P4. How am I getting these dimensions? These we have explained in detail in the last lecture. So here total number of scalar multiplications will be P1 into P2 into P4. What is the next possibility? The second possibility is that split is happening after A3. In that case, first part will be dp of 2, 3. Second part will be dp of 4, 4. And what about the third part? After dp of 4, 4, the third part will be dimension of A2, A3 will be P1 by P3 and dimension of A4 will be P3 by P4. So when you multiply these two matrices, resultant number of scalar multiplications will be P1 into P3 into P4. This is what we learned. So the next step, let us find out the values. This will be minimum of, what is dp22 from a dynamic programming table? dp22 is 0. So 0 plus what is dp34? If you check this table, dp34 is 120. 120 plus P1, P2, P4. What is the value of P1, P2, P4? If you see here, the value of P1, P2, P4 is 15 into 3 into 4. So you should write here 15 into 3 into 4. Then what is the second one? This part, dp23. dp23 is here, it is 450 from this table. So dp23 is 450 plus what is dp44? dp44 is 0. So dp44 is 0 plus P1 into P3 into P4. If you go here, what is P1 into P3 into P4? 15 into 10 into 4. So this will be 15 into 10 into 4. Let us complete this calculation. Minimum of, what is this? 15 into 3 is 45 and 45 into 4 will be 180. So this is 180. 180 plus 120 will be a total of 300. And what about this one? Here 15 into 10 is 150. 150 into 4 will be 600. So this is 600 plus 450. This total will be 1050. So what is the minimum among 300 and 1050? It will be 300. So the value to be inserted in dp24 is 300. dp24, the value to be inserted is 300. At this point, we have only one more block to be completed. And when we complete that block, we'll have the final answer. That is, what is the minimum number of scalar multiplications using which you can multiply all the matrices from A1 to A4. So let us do this final step. In this case, it is getting slightly more complex and I want you to see how it is getting complex. That is why I specifically took 4 matrices. So length is equal to 4. Let me erase these things off. these erased off. Okay, so now we'll take the final case. Be careful here. Final case, we are having 4 matrices. So what are the possible splits? When you have 4 matrices, then splits are 1, 2, 3. 3 possible splits, or the values of case are possible. Let us take the first one. So you have matrices A1, A2, A3, A4. These are the 4 matrices you have. Possible splits are k equal to 1, k equal to 2, k equal to 3. These 3 are the possible splits. So how will your recursive relation look like? Your recurrence relation will look like this. Your dp14. How are you going to fill this value? This value will be minimum of, what are the possibilities here? First thing is that split is at 1. So if split is at 1, first part will be dp of 1, 1. 1, 1 plus second part will be dp of 2, 4. From 2 till 4. That is what 2, 4 means. dp 2, 4 plus third part is about scalar multiplications. After you have a1 and a2, a3, a4, what is the number of scalar multiplications required to find final answer? Size of a1 will be p0 by p1. Size of the result of a2, a3, a4 will be p1 by p4. So what will be the total number of scalar multiplications? It will be p0 into p1 into p4. So this is the first case. Second case is that minimum of all these things we have to take. Second case will be that the split is at k is equal to 2. If split is at k is equal to 2, your first one will be dp of 1, 2. This is the first part of your split. Your second part of split will be dp of 3, 4. This is the second part of your split. After this, what will be the total number of scalar multiplications? A1, A2 will be of size P0 by P2. What about A3, A4? It will be of size P2 by P4. So total number of scalar multiplications will be P0 into P2 into P4. This is the second one. In this case, one more split is possible. That is, after this, there is a k equal to 3 split. In case of k equal to 3 split, first part will be dp of 1, 3. That is including these 3. Second part will be dp of 4, 4. So this will be dp of 4, 4 plus what will be the remaining number of scalar multiplications? A1, A2, A3, this will have a dimension of P0 by P3. A4 will have a dimension of P3 by P4. So here total will be P0 into P3 into P4. So this is the final one that you have to find. Minimum of all these. Let us take each of these values. Let us find this out. This is equal to minimum of what is dp11? Let us go back to the table. dp11 is 0. So this will be 0 plus what is dp24? dp24 from table is 300. So this will be 300 plus what is p0, p1, p4? p0, p1, p4 will be 5 into 15 into 4. So this will be 5 into 15 into 4. Second one is dp12. What is the value of dp12? It is 225. From the table we know it is 225 plus dp34. What is the value of dp34? It is 120 plus p0, p2, p4. What is the value of p0, p2, p4? p0, p2, p4. 5 into 3 into 4. So this will be 5 into 3 into 4. And what is the third one? Third one is dp13. dp13 value is 375. So we have 375 here plus dp44. dp44 value is 0. So that will be 0 plus what will be p0, p3, p4. This value will be P0, P3, P4 will be 5 into 10 into 4. So that will be 5 into 10 into 4. How can you further solve this? If you solve this, you will get this is equal to minimum of 5 into 15 will be 75. 75 into 4. So that will be 300. So 300 plus 300, this will be a total of 600. What about this one? Here you have 225 plus 120 plus what is 5 into 3 into 4? 5 into 3 is 15 and 15 into 4 is 60. So you have this as 60. 60 plus 120 is 180 plus 225 will be 405. So you have 405. What about the next one? Next one, you have 5 into 10 into 4 here. That will be 50 into 4, which is 200. So 200 plus 375 will be 575. This will be 575. Totally, minimum among 600, 405 and 575. Which is the minimum value? It is 405. This means the entry at DP14 should be 405. So we should write 405 here. What did we understand from this? I told you whichever is the value at the top right block, that will be the final answer. That is minimum number of scalar multiplications required to multiply matrices from A1 to A4 will be present in the block DP14. So whenever you reach the block that is at top right corner, that is when you find the final solution. So here 405 is the minimum number of scalar multiplications using which you can multiply these four matrices A1, A2, A3, A4 if the dimension are as given below. Depending on the dimensions, it will change. So for these four matrices, you cannot multiply these with lesser than 405 scalar multiplications. This is what it means. So this was a complete illustration of matrix chain multiplication. How can you multiply these matrices, which is a sequence of matrices, and what is the best way of parenthesization? One more thing is that you might be thinking that we found out the minimum number of scalar multiplications, but how do we know what is the best way of parenthesizing? That is, you know minimum number of scalar multiplication is 405, but you don't remember whether it came when you did A1 into A2 into A3 into A4 or you did some other parenthesization or whatever. So one thing you have to keep in mind is generally in matrix chain multiplication problem, the final answer expected is the minimum number of scalar multiplications. But if you want to find the best possible parenthesization possible, that is, in order to get this count for scalar multiplication, what should be the way of parenthesizing these matrices? If you want to find that, then along with this matrix, you should maintain one more matrix. That matrix let us call as S or something. That matrix will be of the same size, and instead of entering these scalar multiplication counts, you should be entering the split, that is whichever is the k for which you got minimum value. See, for each of these values, for each case we found the final. Among them we chose whichever is the minimum. So in this case, for example, we had k equal to 1, 2 and 3. For k is equal to 2, you got minimum. So for each of the split, while you are storing the scalar multiplication count in this matrix, the dynamic programming table, keep one more table in which you will keep the split. That is, instead of 405, you will be entering k is equal to 2 here. So if you have the splits, then you can easily backtrack and find out exact parenthesization that is required. So the major task in matrix chain multiplication problem is to find the count of scalar multiplications. So that is what we have found here. In the next lecture, we will see how to write code in order to get this done. We already understood the algorithm. In this lecture, we went in deeply, in detail through how exactly is the dynamic programming table getting filled. Next lecture, we'll be seeing the we'll be seeing how to write code. So that will make it complete from end to end, from starting what is the problem, what is the algorithm, then how exactly is that algorithm working in the backend, that is inside the DP table, that also we learned. Next lecture we'll be learning how to write code for this. That will make it complete.